for today, we are going to practice the same quantitative variables, okay, but we do comparisons, okay, doing the comparison between 3 or more than 3, okay, independent or dependent groups of data, okay, of a variable, okay. All right. Okay. 3 or more than 3 dependent or independent groups of data of a variable, or let's say more specifically, quantitative variable, right? An example, you can say, for example, yeah, salary. Okay? So salary, you want to compare the salary between different categories of job, okay, or between 3 different region, okay, or between 3 different companies, right? All right. Or age, okay, and etc. Okay, right? And we are doing correlation between 2 or more quantitative variables, right? So this is what we are going to do. And if we have time, we will work on some of the comparisons, okay, comparisons of 2 or 3 groups of qualitative variables, okay. All right, okay. So these are the focus that we are going to work on today. The first 2, we will have time to do and to practice, all right? For the third one, if we have time, I mean, if the time permits, we can do this, okay? All right, so please have your computer ready and please open your R program, then we can work together, right? So this is my R program, all right, okay. This is another one, okay. So today we practice the Kruskal-Wallis, okay, Kruskal-Wallis and Friedman test. Okay. Kruskal, okay. So Kruskal here, in short, Kruskal-Wallis, okay. KW, okay, just KW, and Friedman here, Friedman FM, all right. So Kruskal-Wallis, we used to compare the distribution of data measured by the central value, meaning the rank sum, okay. So we compare the rank sum of groups, okay. So here, what is it? Anyone, please? Please let me know of how many groups, dependent or independent groups here. Anyone, please?
Maybe 3 or more groups, sir.
Say that again, please.
3 or more groups.
Okay, 3 or more group. Thank you, Brian. 3 or more group. So 3 or more. But please indicate one more thing: dependent or independent groups. Dependent or independent groups?
Independent.
Thank you, Donna. So it is independent group. All right. So when we use Kruskal-Wallis, okay, Kruskal-Wallis, the sample must be taken from different group, okay, not repeated group, not dependent group, not paired group, okay. So you have to remember. And of course, the data we have already talked, it is not normally distributed, or we can say that the normality of the data is not met, right? So for the FM, okay, Friedman, we used to compare the rank sum of dependent, okay. So this is what we need to understand, and we need to also remember, all right? Okay. In this class, we are going to use the data cars 93 again, okay? The car data 93. nè thông này một đây là mình ở đấy trong nhóm chat một nhưng chơi giờ này hay chơi giờ được bắt không? Okay, sorry for a bit of the communication here. Okay, the data that we use today is also the car 93 in the library mass. Okay, so first we need to load library mass. Okay, together, please. Okay, and then we say data. Okay, data car 93. Okay, and to be short for us, easy to call, to do some subsetting or to do some operation, we can represent our data or we can rename our data car to be a df. Okay, and as we understand from previous class, when you see on the upper right panel, you see cars 93 having 93 observation of 27 variable, and they are the same as the df because df is a clone of car 93. Okay, and we want to check some of the names or the head we can do. Okay, so name of df we can see here. Okay, the variable names df here we have manufacturers, we have model. Okay, and we have type, we have price, min price, max price, cylinders, engine size, and so on. Okay, in order to know like the measurement of each variable, we can also use a function, say like s apply. Okay, s apply here, and then our df and the function here we say class. This function will show us the class or the measurement, the categories of each variable. You can see here. Okay, so manufacturers, model, type, and min price. Okay, so manufacturer is a factor, model is a factor, type of car is also a factor, min price, max price, MPG city, MPG highway, they are numeric. So if they are numeric or they are integer, they are in the group of quantitative. Okay, or we say, let's say scale, right? If it is a factor, okay, if it is a factor, it is a nominal. Okay, it is a nominal variable. With that nominal variable, we can also have a deeper look. Okay, that whether that nominal data has an order or not. If there is an order of each variable, we can also divide it into an ordinal. Okay, so this is the function to show us, okay, the measurement of the data. Okay, all right. Okay, and when we see what are the data here, what are the numeral or not numeric, or they are qualitative or whatever, the focus for us today is to do comparison of quantitative data that do not meet the normal distribution pattern. Okay, so we have to check the normality of the quantitative variable inside the data df. Okay, all right. Since we have worked on it quite long ago, okay, I have noted, okay, I have noted that some of the variable represented by number here, okay, they are the quantitative. So just to be quicker, okay, and you can see the p-value of each variable based on the Shapiro test. Okay, please tell me again, if the Shapiro test, the p-value indicate a value of less than 0.05, so the data has a normal distribution or not normal distribution?
Not normal.
Okay, good. So if the p-value of Shapiro test is smaller than 0.05, then the data is not normally distributed. Okay, and therefore it meets the assumption of the non-parametric test that we are going to focus today, such as the Kruskal-Wallis and Friedman. Okay, and I noted for another one. Okay, so the data that do not have a normal distribution. Okay, I have a note already here. So the df I subset for the data that do not have a normal distribution. Okay, so df nn, okay, non-normal. Okay, let's say nn here, double n is non-normal. So I run this again. Okay, and you can see from the above. Okay, the three price variable, are they normal? The three price, min price, price, and max price, are they normal?
Not sir.
No, not at all, right? So to be clear, not confused, you can say, you can copy this, okay, and make like this. All right. So this, okay, Okay, yeah, and some more. MPG city, MPG highway, engine size. Are they normal?
No, sir.
No. Okay, so we can just copy the names of the variable. So when we use the name of the variable, it prevents us from confusing when we use it. If we use just number to represent a column, somehow we miss typing, and it also makes us or leads us to an errors. Okay. Okay, so I just copy, then make it clear. All right, and we check again. Okay, not yet this one. Okay, let's check others. Okay, so horsepowers, RPM, okay, route per mile, which are not normal among the three.
Horsepower.
Good, horsepower. Okay, so I copy this one. Okay, horsepower. Okay, and others. Okay, so wheelbase, width, tune circle, which one among the three is not normal?
Width, sir.
Good. All right. Okay, and the last row. Okay, this one, which one is not normal?
None, sir.
None, sir.
All right, good. So that's all for us. So we have this. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so DFNN, the DF non-normal distribution data. I execute. Then you can see on the upper right here, DFN, it has 93 observation with only 8 variable, quantitative variable, but they are not normally distributed. Okay, so these are the data. Okay, right. So I just close it, go back. Okay.
Okay.
All right. So now we have the quantitative variable, but not normally distributed already. So we can further go to the comparison, doing the analysis using the Kruskal-Wallis and the Friedman. In our data set, like we known before, okay, it is a record from 1993 about the car sales, okay, in just that particular year. And therefore, we don't have the dependent sample at all. We don't have the pair sample or repeated sample at all, okay? So in this case, we can only use Kruskal-Wallis for this data for our car 93. If we want to use Friedman, we refer to the data that are dependent on one to another. So we have to create or to assume another variable. Right. So let's practice. So we want to do comparisons of one variable. Please take one variable among these. Anyone, please pick one variable. Okay.
Horsepower.
Okay, horsepower. Okay. Practice on horsepower. Okay. Horsepower. Okay. So we need a factor variable, a nominal variable that divides the horsepower into 3 or more than 3 groups. Okay, all the factors variable. Okay, we have seen from this one. Okay, we have make. Okay, origin. Do you remember how many origins of the data?
2, sir.
Only 2, yeah. US and non-US.
USA.
Yeah, right. And how about the
Airbag, sir.
yeah, airbags? What about the airbags?
3 groups, sir.
Okay, so let's say the airbag, right? So airbag. Okay. For the Kruskal-Wallis test, we can analyze using the R program-based library named stats. So if you don't load that library, it is already there. Okay. But if you want to use, for example, the R statics library, it is more. We can do many operation on the library or statics. It's another way as well. Okay. But if not, we just use the function on the library state. Okay, library state in the R. Let's say Kruskal here. Okay, Kruskal test. And the Kruskal test, if you want to know the argument, okay, the argument inside, you can make a question mark, ask the data to, ask the program to help explaining us here. Kruskal-Wallis rank sum test. Okay, rank sum test. So Kruskal test. And then we can see the example or the default method here. X refer to the dependence variable, the quantitative variable that we would like to compare. And G, it is the group, the nominal variable that divides the X into groups. Okay, in this regard, 3 or more than 3 groups. So R is practical because with each function, there are a lot of examples. Okay, at a very low down here when we type question like that. Okay, because there are so many function written in R from day to day, so many functions. So it is hard for us to remember. In this case, we can ask the program to explain us, right? So their example here, you can just copy the code, okay, and then you paste to your editor and execute. You get the explanation, the result, all right? Okay, so we have here the quantitative variables that we are doing is the horsepower, okay? So horsepower, okay? So horsepower here, okay? Just prevent the wrong spelling, okay? So the horsepower divided by df, airbags, okay? Airbags, okay? So we delete the question mark, okay? So this function is in library start, okay? So this library start is a built-in with the R program, program. So you do not need to load it, okay? You can run, okay? This is our result, right? So anyone, please interpret the result. Anyone? So quiet. Anyone, please?
There is a significant difference, sir.
Okay,
There's
there
a
is.
significant difference in the horsepower between.
Okay, right.
Significant difference in the horsepower.
Okay. So here I do not show the null hypothesis, the alternative hypothesis anymore, right? So we have discussed this like during the previous session already. So we just go straight to the meaning. Okay. So here, meaning, I just write in short. Okay. A significant difference is detected. Is detected between, okay, horsepower of the 3 airbags car. Okay. Right. You can also do the new function. I mean, not new, not in another function with the all static library. Okay. We can do it in using the function in our static library. Okay. So you need to load library R static. Okay. Here. Right. So with our static library, it helps us many operation. Okay. It helps us with many operation. Okay, so we can use like df, okay, and this sign. So this sign means that all the output from our execution is taken from the data df by doing the operation on the next right of this sign. Okay, all right. So once again, it is the output that we do the operation using the data that is at df. Okay, by doing the operation on the right function of the sign. Okay, so here the function that we are going to use is Kruskal test. You can see here Kruskal.test in stats, all right? But in R static, it is Kruskal_test. Okay, so here we do not have to use the subtraction of the data anymore because we have df in the very front. So we just put the name of the variables that we want to do the comparison. In this case, first of all, the names of the quantitative variables that we want to compare, and then this sign, okay, this correlation sign with the nominal variable. In this regard, it is airbag. All right. Okay. And after that, you can run. Okay. So here is the p-value. Okay. The p-value. Right. Let's see if there is a different or no different. Okay. Right. So here the p-value from the function in the R stated library, and here is the p-value from the start library. Different or no?
No, sir.
No, not at all, right? So here it's just it's just a round up 788. Okay, here is round up 788 is 79. Okay, here DF the same too, okay? And the Kruskal-Wallis chi-square is the same, okay? So here is a round up 24.5. So 499 rounded up to 5, okay? So they are the same, right? Okay, so this is the result of Kruskal-Wallis. And remember, whether we are doing ANOVA, repeated ANOVA, Kruskal-Wallis, or Friedman, if the overall result indicates a significant difference, then we need to do the post hoc test, okay? We need to do the post hoc test. So we need to do post hoc, okay? Post hoc test. And for the post hoc test, in the non-parametric test, we use the Wilcox or pairwise Wilcox test. For the parametric test, we use, okay, the pairwise T-dot test. There are many others pairwise tests that you can use as well. For example, the ANOVA. One of the well-known post hoc tests is the Turkey, HSD, I mean. Have you ever heard that? The Turkey SHD test, the post hoc test, okay? But you can use just the pairwise t-test for parametric test. For the non-parametric test, you can just use the pairwise Wilcox test, okay? All right. So doing the plot, okay? Box plot, and then here, okay? DF, okay? Horsepower with the DF airbags, and you can use colors like 2 to 4. You can use Y lab equal horsepower, okay, powers. The X lab equal air bags. Okay, right, and can also run. Here it is our result. Okay. Okay, now let's check how much you gained from our previous understanding. By just looking at our box plot here, I would like some of you or just one of you to make a hypothesis whether there is a pair differences among the three. Anyone would like to guess based on our box plot here? Okay, so the car, okay, built with the airbag for driver and passenger, they have a stronger horsepower with the driver only, okay? So not really strong. But if the car built with no airbag, so the horsepower is not that strong compared to the other two, because perhaps they think about the security. If there are no airbag and the horsepower is strong, then it may have a high risk when having accidents, right? So please give me your hypothesis whether there is at least one pair difference or two difference or three differences. Any wild guess, wild hypothesis or intelligent guess? Anyone?
Can you repeat the question, sir?
Okay, thank you, Brian. So I just want to check from your understanding from the previous discussion by just looking at the box plot that we have that you see on the screen. Can you provide a hypothesis whether there is a pair difference, okay, between the car with driver's passenger airbag just and the driver only and the car with none airbag, okay, in terms of horsepower? Simple like this. Okay.
I would say that there is a significant difference between the airbags of those, the driver and passenger, compared to the driver only, as well as a significant difference also comparing the airbags of the car with driver only and without the driver.
So two pairs differences.
Yes,
right?
and maybe and there is also a difference between the driver and passenger, both with those two and compared to those that have none at all.
Okay. So you assume or you expected that, okay? There are three pair differences, okay? Let's say the red one is number 1, the green is number 2, and the blue is number 3, okay? So the first pair, 1 and 2, there is a significant difference, and the second pair is 1 and 3. There's a significant difference, and the third pair is 2 and 3, okay? So I got 3 hypotheses from Brian. The 3 pair will be significant different, okay? Is there any like different expectation, or you all agree?
All agree, sir.
Okay, just agrees.
Brian.
Okay, good. All right, let's say. Let's see. Okay. So here, okay. For the pairwise, okay, Wilcoxon test, the same as the overall Kruskal-Wallis, we can use the function in the start library or in the R static library. The result is the same. Now let's do both of them. Okay, Wilcox. Okay, no, we start with pairwise. Okay, pairwise. See here. So the pairwise t-test for the parametric test, pairwise Wilcoxon for the non-parametric test. Okay, so X and G, right? X and G, p-adjusted method. Okay, so X, our X here is ds horsepower. Okay, here. Okay, and then the p-adjusted value. Okay, so in this, okay, in this function pairwise dot Wilcox dot test written in the start library, the default, the p-adjusted method is home. Okay, and the pair is foul, meaning that they are not dependent. Okay, the three group are not dependent, right? So let's write in full. P-adjusted method. Okay, you can use home, but if you do not use home, it is automatically calculated with the home because it is a default method. And pair here equal foul. Okay, F. And even like I state, okay, even you do not put these two arguments. If you run without these two arguments, the result is as same as this argument when you include it because it is a default, right? So now let's run. Okay, here. So there is a warning message. Okay, but warning message here is okay, no problem, don't worry, because the data inside somehow there is a duplicate value. For example, sometimes it has 2 and other sample also has 2 value. So here, so because of that, right? So it's okay. Let's see. So driver and passenger here, the red one, with the driver only here. Okay, driver only. So the p-value is 0.008. Okay.
Yes, sir.
Right. So number 1 to number 2, number 1 to number 3, driver, passenger, and with the none. It's also significant. Number 2,
Yes, sir.
yeah, driver only with none here. Okay. So
Significant.
significant, all significant, right?
Yes.
And you can see here the method is home. All right. Now let's run again without these two argument. Okay. You don't use these two argument. Okay. So they are the same. Okay. So this is the default function. If you do not put it, it automatically include in the code. Right. We use with the R static. So these are the state library. Okay. And here also state library. You can say significant different, right? Okay. So another one, we use here df and then the sign percentage bigger. And then we need to say the group by. Okay, the group by. Group by, it means the nominal function that divides our tested variable into groups. So in this case, group by the name of the variable. So the nominal variable here, what is it? What is it?
Horsepower and airbags.
So the grouping variable is, airbags. All right. Okay. Okay. And then we need to state, okay, the variables, the next variables that we want to test, and using the pairwise, okay, pairwise Wilcox test here. Okay, pairwise Wilcox test. In R static, it is underscore rather than dot. Okay. All right, and the inside is the tested variable, the variable that we want to use. Okay, we want to use. So here it is the what is it? The horsepower. Okay. Right. So you can run, and here there is an error, meaning that our code is not right. Okay. So it is not right. So we need to check our code again, right? So if we want to do group by, it means that the pairwise is do in 1 by 1. Okay. We have no pair to compare with. Okay? In this regard, we just put the pairwise here, and inside the pairwise Wilcox.test, we need to put a relation sign here. Okay, with the nominal variable that group, okay, our data into 3 groups. Okay, so in this case, it is airbags. Okay, with the R static library, we need to also include the p-adjusted. Okay, p-adjusted here. Okay, because there are many, we put home. Okay, right, and we can just run. Right. Okay, so here is p-adjusted. Okay, p-adjusted value. We use the home here. Okay, it is the result. Okay, here, how is it? So the first one, okay, driver and passenger with just driver only, significant. Okay, and driver and passenger with none. So 1 to 3, it is also significant. Okay, with the driver only, number 2 to number 3, green to blue, it is also significant. Okay, all right. So please check here. Is it the same or different? Okay, so 1 is driver and passenger. Okay, driver only is 2, none is 3. I just name it 1 to 3. Okay, so 1 to 2 is here 0.008. Is it the same here? It just rounded up. Okay.
Yes, sir.
Right.
Yes, sir.
Okay. So when it rounded up, so 4 here is omitted. Okay. And here 1.7 the same.
Yes,
And
sir.
here 2, yeah, the same. All right.
Yes, sir.
Yes,
Yeah.
sir.
Okay. So you can use either the function written in the start, the base R library, or the R statics. Okay. All right. The important that we use the R static is that we can also run at a time when we do have the subset. If you want to do subset, for instance, in terms of origin, we have 2 subsets, one in the non-US and another one is in the US. So if you want to do Wilcoxon for the data only in the car made in the US, you can also use this one very good one, very good code. Okay, like here, you don't have to make a subset, one DF for non-US and another DF for the US car. You do not need to do so. You just use the R static here, and then you can get a result of the Kruskal-Wallis between the horsepower among the 3 types of airbag in the non-US car and as well as in the US made car. Okay. You want to see example? We can do here. So here, doing Kruskal-Wallis for the data for 2 subset data based on origin or region here. Okay. Okay. So we just need to know this one. Okay. So Kruskal-Wallis, you can copy here, and then you can type. And after this one, after this operator, we can use group by, and then origin. Okay. It means that the Kruskal-Wallis here will do it for us. One for the data in the non-US, and another one is in the US made car. Okay? So that is easy because it provides us 2 results at the same time. Okay, so we can run here. See, so for the car made in the US, there's also a significant difference in terms of the horsepower. Okay, and for the car that made outside the US, is also a very, very significant difference. Okay, among the car with different horsepowers. Okay, right. So we can use we can get a result for 2 data set or 3 data set at the same time, just one click. That is one of the advantage of the R static. Okay. Questions so far? If not, I would like to have one of you to practice sharing screen and doing the Kruskal-Wallis here. Pick any variable other than what we practiced here. Okay, just one variable, different variable. Anyone want to try? Want to share to your class? Make sure that you know how to interpret the data. I mean the result, right? How we interpret it based on the p-value here. The first step, we have to look at it. And then seeing the p-value, you have to think back about the null hypothesis and the alternative hypothesis. Otherwise, you may get lost. Okay. Okay. Right. Now, any one of you would like to try sharing your screen and doing a Kruskal-Wallis test using your variable that you want to work on? Please.
Me, sir.
Ryan, yes.
Let me
Yeah,
try.
Ryan. Okay, thank you. You can share screen or not, Ryan?
Let me try, sir.
Okay.
Share screen.
All right.
Can you see my
Yeah.
screen, sir?
Yeah, yes. Okay, good.
So now we're going to compare. Should I, ano, sir? Should I select the same variable or not, sir?
No,
from
please,
our-
the different quantitative variable that we want to compare. Okay, but for the nominal variables that divide into 3 or 4, you can use the same airbag or any other variables.
Okay, sir. So
Okay.
let's do some comparison of price, sir. Let's say
Okay.
price.
Yeah, right.
Compared to the airbag, sir.
Mhm.
Okay, so first you have to do is to do the pairwise thing.
So first, we need to do Okay, general Kruskal-Wallis. Because airbag,
Yes,
we have
sir.
different types, three groups.
Yes, sir.
Okay.
Should I use the normal, sir, or the R-statics library?
Anyone you like,
Yes.
anyone, no problem, because it provides the same result.
Pairwise Wilcox test.
Mhm.
Then BF, and we'll select price.
No, first do the Kruskal-Wallis first.
Okay, sir. Okay, sir.
Yeah.
Sorry.
If the Kruskal-Wallis do not show a significant difference, we do not need to do the post hoc pairwise. Okay. Okay, Kruskal test, good. No different, not horsepower is price.
Yes, sir.
Yeah, yeah,
Sir.
yeah,
Okay, first.
good.
So let's run this one, and we have here the p-value of 0.0000008,
Yeah, yeah.
which is very smaller than the 0.05. So there is no, I mean, there is a significant difference
Yeah,
between the price and the of the cars with the airbags, sir.
okay. So can you do a box plot showing which type of car of airbags have higher price? You can see.
Okay, so let me just
right.
write this right here.
Yeah.
Okay, so let's do some box plot.
Mhm.
Airbags. So let's use the codes from earlier.
Yeah,
We have this one here.
yeah. You just type a different y
Yeah.
axis. Y axis is price.
Like this for
Yeah.
price.
Yeah.
Okay, so let's run this code.
Okay. So-
okay, sorry. There's an error. Yeah,
Yeah,
I
too
forgot
small.
to the. Alright, so
Okay,
here we have
good.
this.
Can you make it bigger vertically?
Alright, so here we have the bus plot showing the difference between the prices of the different cars. No, some cars have some cars with driver passenger have airbags. Some also have the driver only and
Mhm.
none. So this shows that there is.
Can you make the box plot longer vertically? Vertically longer?
vertically? Yes,
Yeah,
sir.
yeah, good.
How about
Our
this
box
one?
plot, our box plot, the graph.
Okay.
You can drag it up the middle, Yeah, this is
Okay.
okay. Yeah,
Alright.
okay. Yeah. So to me, the three pairs, okay, the price of the three pairs also significant different, and you can see, okay, we detect a general significant difference in terms of price among the three types of car having different airbags, right?
Yes, sir.
And we can see that the car that were manufactured for both drivers and passengers airbags have higher price, right? Significant
Yes, sir.
higher price. The red one.
Yes, sir.
For the non one is very low, so they do not need effort to put the price on the no airbag. So yeah, it is logical. Okay, then okay, everyone just need to remember that if a general result shows significant difference like this, whether you're comparing 3 groups or 4 groups, okay, as far as comparing more than or equal 3 groups, if there is a significant difference in the overall model, you need to do a post hoc. Okay, and for the non-parametric test, we can use the pairwise Wilcox. And for the for the parametric test, we can use the pairwise t-test. Okay, in this regard, Ryan can do the next one.
All right, so let's do some. Since there is a significant difference, we should do the post hoc thing.
Right. Yeah.
Okay, so let's use the pairwise.
Mhm.
I have copied it already, so let's just paste it, sir.
Okay. Good. Yeah.
All right, so let's change the horsepower variable to the price.
Mhm.
This is what we are using now. So the same DF airbags, the adjust method is home, pair is false. Let's run this code.
Mhm.
Okay, so here's our result.
Mhm.
Compare with the driver and passenger only to the driver only, the p-value is 0.41, which is smaller than the p-value.
Yeah.
So there is a significant difference, sir.
Yeah. Right. Right. So
compare
yeah.
with- Yes, sir. And
pairs.
looking at these figures or these numbers,
Mhm.
we can see that these numbers are significantly lower than the p-value at 0.05. Therefore, the three comparisons are there is a significant difference, sir.
Okay. Good. Okay. Right. Yeah. For your real practice or for your project, research project or thesis, yeah, when you get this, so you need to state your variable. For example, your like a student performance or your student score between class A, class B, and class C. Which one is significant higher? Which one is significant lower? Okay, so you have to state it more specifically, not just only significant different. All right. So significantly different is one, and a deeper step is to include the explanation of the variable you are doing the testing. Okay. All right. Good. So now let's do the Friedman test. Okay, just a reminder. Okay, Friedman test is used to compare the rank sum of 3 or more than 3 dependent groups or repeated data. Okay, we can say repeated measures. Okay, repeated measures. Okay, so this is what we are focusing on. All right, and let's say that we are going to have a practice on four groups. Okay, represented by 1 nominal variables, and in this case we are not using the data car93 again. We are creating. Okay, we are developing, okay, generating a data set. Okay, for us to understand the quantitative variables that we are working on, let's say score, okay, student score. Okay, now generating the score, I use one libraries that can help us generating the not normal distribution data. Okay, so the library is called, okay, let's say here again. Okay, the data is generated using a function in the library, the detect. Let's see here, what's it? Library, the norm. So I just remember the function. It is called air none norm. Okay, air none norm here. So air means random, and none is not. Norm is normality, normal distribution. Okay. So it is detect norm. Okay, in the library detect norm. Right. So I load the library detect norm. Okay. If you do not have, please install. Okay, this detect norm. Okay. So please go to package and then install. Okay, and type detect norm here. Okay, click on it and click on install. Right. For me, I installed it already, so I just load it into our working environment and then I run it. Okay, so it is already here with the library norm. Now let's download and check if it works for you. Okay, check it, download it.
Still downloading, sir.
All right.
Downloading. Downloaded and run, sir.
Okay, everyone, download it. If you download, please write library detected. Library detect norm and run. And on the console on the lower left here, if there is no error, you can load it and no error, so it works. Okay. So let's generate the quantitative var name score. So score here can be any score, student score, or your score, or whatever. Okay. Okay. Score that is not normal. Be distributed. Okay. So I say score equal R none norm. Okay. And the function inside n, and here you can see n is number of samples that we want. Mean, it is the average that we want, standard deviation that we want, and the q is positive q or negative q you want, and the Curtis you want, right? So I just here, so n equal, let's say 100, okay, and mean, so score, let's say the band is out of 10. So the mean equal, like say 7, and standard deviation, let's say 1.5, and Q's, Q, let's say like 1, and Curtis, okay, say 0, okay. This is score from here, okay, 100 sample. Okay, you can run, okay, you can already get a score. However, this, okay, this function results in two, it will result in two data. You can see on the upper right here, it is called dat. That it is the data that we generated, and the other one is Flashman curve. The method that it is used to generate the data, the not normally the data that we want. Okay, so in order to get our score as a quantitative variable, you need a $sign here in order to extract just only data. So let's say that, okay, because score here, it has two results. The first is the data that we generated. The second one is the method to generate the data. What we want is not the method, okay? We want just the data. So we just need to set a $dot here, okay? And now we get the score of 100 students here, right? Now let's check whether this score is normally distributed or not. Please tell me what function we want to test. We want to check. We use to check Shapiro and then score. Okay. All right. Here, the p-value of the Shapiro is here. 1.2 power minus 6. Bigger or smaller than 0.05. And if it is that, normal or not. So score we test already. Okay. It is just a variable that we are creating. And we test the normality. Getting the result of the p-value is here. Okay. 1.2 power minus 6. Which is smaller than 0.05. If it is like that, the data is normal or not normal.
Not normal, sir.
Okay, Brian said not normals. And okay, everyone, not normal, sum up. So that I can see that you're with me or with the class. Okay. Ellie, Farah, Cedric, Yugarito, Shanelin, Rachel, Joyce, Shanna, yeah.
Normal, sir.
Okay, so, okay, please understand that, right? So if the p-value of the Shapiro is smaller than 0.05, the data is not normal distributed, not normal, okay? Okay, you can also check the histogram. Let's say hist, okay, and then score a variable. You can see here, right? It is a positive Q. The tail is on the right here, okay, the tail is on the right. Most of the data is in between the mean. The mean we set is 7, but because it's not normally distributed, our generated result mean around or between 6 and 5 and 6 here. Okay, so this class has frequency of maybe 27, 28. Okay. All right, so I have one score, and this one score is obtained from 4 times of testing of the student. There are 25 students that are tested 4 times. Okay, so I create a nominal variable that is representing the time, okay, of testing, T1, T2, T3, and T4, right? So here, testing time, okay, let's say times, okay, times, okay, time test equal, I say, see, concatenate and rep. So I rep 4 categories, okay, say T1, and yes, T1, then T2, second test, and T3, and then T4, okay? And each, okay? And each appear. So each equal 25, okay? That check is my code is correct, okay? I do not run yet, I just check, okay? Okay, they are correct, right? So T1, T2, T3, or I mean T1 here, okay? Right, okay. So I can run now, right? So time testing, okay? If we want to know how many of each, I can say table, okay, table time test. And you can see the below one, T1, 25 student, okay, T2, 25, T3, 25, all right? Okay, so one variables, okay, a nominal wa, okay, or times, testing time. And then I need, okay, I need a variable that indicate the ID of student, okay? So the ID equal, let's say I concatenate rep, so rep 1, 2, 25. How many times? I rep 4 times. I do the 4 application. Okay, let's check whether this is correct. Oh no. Okay, so rep 1, 2, no, not the apostrophe. Okay, so here you can run. So 1, 2, 3, 4, 5, and then 25, and then start with 1, 2, 3, 4, 5, 25. 1, 2, 3, 4, 5, 25. Okay, so student ID. Okay, right. So from each variable, I I create a data frame combining all the three. Okay. So here, so I say df score. Okay, or df se score. Let's say C bind. C bind, you mean column bind, to make each of the variable arrange in a vertical order. So I C bind the ID, okay, and then time testing, and then score. Okay. Or we can say as data frame, make it a data frame. Okay. Right. Let's check. Our code is correct. So ID is not correct, meaning that I have not run ID. Okay. So I check it again. All right. So we get our data frame. So the first one is ID, student number 1. Okay. Test first time, score 6.7. Student number 2, number 3, until number 25 here. And then second test. And then third test. And then fourth test. Okay. All right. So we have our DF score. It is also registered here, I think. Yeah. You can check here if when we run, it will be registered. Okay, here. All right. Okay. Now we have the score that we obtain from 4 times of testing student. Okay. First time, second time, third time, and fourth time. So is it a repeated or like a dependent measure, dependent sample, or independent, the 4 group? The score is divided into 4 groups. First group obtained from the first testing. The second group obtained from the second testing from the same student. The third, the fourth is the same. It is the score from the third and fourth time tested from the same student. So these data, are they dependent or independent?
Dependent, sir.
Right, they are dependent. Depend on the student. If the student work hard, okay, the second, the third, the fourth test, they may get a higher score. Okay, so the dependent measure, first condition, met our criteria of using the Friedman. Another criteria is that the data of each group, the first group, the second group, the third group, and the fourth group, must be not normal distributed. Okay. For the overall result, I mean the overall for all the data, 100 sample, we have checked already. They are not normally distributed, but to make sure, we can check for each group. Okay. But from my experience, if the overall data is not normally distributed, then when we divide it into groups, each of the group may have not significant, I mean, may not normally distributed. Okay. So we can check using t-apply, or we can use the function in R static. Okay. So let's say in the R static, so df score, okay, sign, and then group by time test, okay, time test, and then okay, we use the Shapiro on what variable? Score. Okay, let's see. Okay, unargument, where is score? Let's see if they are correct. Score, time test, the group by time test, and then Shapiro score. Error in Shapiro test score. First round. Okay.
I think that the one that we should use, sir, is the Shapiro underscore test.
Oh yeah, that's great, Brian. Okay, so it is in the all static, it is underscore, not the start. The start is dot. Okay, good. All right. And still errors. What's wrong? Let's see. Dollars. The did group by time tested. Then here, where the errors occurs. Why is this? Why is it like that? It should be fine. DF, we have it already. DFC, time, score. To see where the error. Shapiro underscore test. Shapiro underscore test and score. Okay, should be fine, yeah. Let's say I can check here. Let's say it is supply and then df score function class. Oh, score is here a character, so it does not work. Okay, here. So whenever you combine, okay, whenever we combine a variable into a data frame, and that variable include the characters here, then this one will be converted to characters. Okay, that's why. So in order to convert it into numeric, we can use this function. Okay, sc $score. Okay, then is equal as numeric. Okay, and then df score. No, df here and score. Okay, so can run. Okay, and let's see, let's apply it again. So you can see here, ID is characters, time is characters, and is now numeric. Okay, let run. Okay, so here T1, T2, T3, T4. Okay, T2, is it normal? T2?
Yes, sir. Normal.
Yeah, T2 is
Normal.
normal, but but the other three is not. All right. So when
Yes, sir.
when doing the non-parametric test, comparing more than one group, 2 group, 3 group, 4 group, or 5 group, if any of the group, if any of the group is not normally distributed, then we have to use the non-parametric test. Okay, the parametric test, it have to meet that the condition that every group, every group must be normally distributed. If there is only one among the group is not normally distributed, then we have to use the non-parametric test. Okay, so now we can go to use our Friedman. Okay, so doing the FM test. All right. Okay. And if you want to know what are the argument in the Friedman test, you can type Friedman test here, the default function in the state, the base state function of R. Okay, here Friedman test. Okay, and this here an example is the matrix, and then here rows, and then you can use down here Friedman test. Okay, or here. Okay, X groups and ID. Okay, and W here, what is it? The W. Okay.
Really?
Hello, what do you mean?
Nothing, sir.
Okay, good. All right, so we do the Friedman test. Okay, Friedman test here. So DF, or well, let's say, what is the name of our tag here? DF score. Okay, we have ID, time, and score. Okay, so our function in the R static is here. Okay, so X and group, and this is the ID, and this is our data. Okay, so we can follow this one. So we have score. Okay, with the sign of the time test, and making the effect by ID. Okay, let's see. How is it? Okay. Friedman bring some test. Okay. DF3. Okay. Is there any significant difference among the score obtained from 4 time of testing? Is there any difference?
No, sir.
No, at all, not at all. So the p-value is bigger than 0.05. Okay, so here's p 0.28. Okay, or like let's say 29, bigger than 0.05. Okay, so no sig diff. All right, so that is the result. Or you can do another one. You can also do another methods. Okay, doing the same Friedman here, different way, but I'm not sure if the result is the same. Okay, so 1 to 25 in another group. So we need to set like this, like SPSS. DF. Okay, so this 26 to 50, and here 51 to 75, 76 to 100. Okay. So this is an error. Okay, this one, the block. You can do with the 3 groups. Okay, like here, but it does not work with the 4 group. Okay, so this is not. We can use with the function in R static. Okay, so DF score. Okay, this operator, and then we need to do group by. Yeah, it is a group by. Let's say Kruskal-Wallis. The same. No, it's not Kruskal. It is the not group by because we do comparison. It's not group by. So let's say Friedman test. Okay, Friedman test here. Our score against time testing. Okay, or we can have a question mark to our code, and then you can ask our testing. Okay, R static here. Okay. So here, okay, so Friedman here, test and ID. So we need to have an ID like this. Okay. Okay. So
Sir,
the
actually,
p-value,
comment, sir.
excuse me.
I have noticed that in the first function that we used, you only use the df and the dollar sign.
This one?
In the previous one, sir. So we can see in the console that the Friedman test df dollar sign score. Isn't it df.sc, sir?
Oh, yeah. You're right. Okay, let's check it again. Good. Okay, it's not the F, okay? It is the F dot score, okay? And then score, DFC here. Let's take a look. Yep. Okay. So 1 to 25. Did you get a result? Is it Brian? Right? Let's see if it works. It is 51 and 75, 76, and 100. Okay. All right. Still, okay. So yeah.
Yes, sir.
So it does not work with this one.
Error 2. Okay.
Yeah. Okay. You can do this one with the start base of R and the R static here. So I can run both of them and check the result whether they are the same or not. Okay. The p value here and the p value here, same or different?
The same, sir.
Yeah. So there is no significant difference, okay, between the score student, even though they are tested 4 times. They are prepared for 4 times before the final exam, but no significant difference. Okay. This is just an example that we generated the data, but in reality, I don't think so. If the student is or are prepared 4 times before the final test, there must be at least a difference, right? There must be at least a difference. But this is a generated, okay, a generated score. That's why it has no significant difference. Then we can do a plot. Okay. So doing some plot here, box plot here, the F score, the score with the F score here of the time test. See here. Okay. So the four group, the 4 testing time, the score are overlap. The difference just only sum of the median. Okay. But the range, the interquartile range and the range are overlapped. So interquartile range, you can see the first and the third quartile, they are overlapped. That's why there's no significant difference. However, assuming there is a difference and you want to do a pairwise test, okay? Let's take a note here, okay? The reality, it is not significant different. But if we assume there is, and we want to do a pairwise test, okay, we can do the following code. But in the real practice, if there is no significant difference like here, then you don't have to. If you do the pairwise, there will be no significant difference. If there is an error. I mean, statistical error, right? Okay, so no significant. Okay. Let's say it is a SIG, and we want to do the pairwise. Okay, but I just make it. But don't do it in the real practice, the real exercise. Okay, so we can do the pairwise. Okay, pairwise. Okay, Wilcox. Okay, Wilcox here. So X group, P adjusted, and the pair. Okay, there are 4. You can copy the previous code. Okay, previous code with the Wilcoxon here. Okay, I mean Kruskal, sorry. Okay, you can do this one or the other one. It's the same. So paste here. So you change the FSC, then pair Y Wilcoxon. This is score. Okay, score and time tested. P adjusted value is home. Okay, and the pair, true or false in this case. F or T. F or T. F or T?
F, sir.
Good, because is it F? No,
Yes,
I don't think so. No,
It's not.
it is dependent because the 4 groups are from the same student. Okay, so it is true. They are pair. Okay, do you all agree?
Yes, sir.
All right. Yeah. Okay, so we can run this test. Okay. So there are 4 groups, and when we do pairwise, there are 6 pair. Okay, here all are non-significant. See, all are none. Like I said, if the overall result is not significant different, then the pairwise will be not different as well. will be not significantly different as well. Whether T1 to T2, whether T1 to T3, whether T1 to T4, whether T2 to T3, whether T2 to T4, whether T3 to T4, they are not significant different, okay? If the overall result is not significant different, okay? Right, and you can do this one as well, the pairwise dot test here, score P adjusted, and then you can put the same thing here, but you need to put like DF, okay? DF SC dollars, okay? And this one as well, then P adjusted, pairs equal true, okay? So there's something wrong. Error pairwise is missing group. So group we already put here, pairwise Wilcox, okay, time. So we need to do this as factors, okay, to make it the factors. Or maybe it's not, it's just only the comma, I think. Okay, none, okay, all none. So we can see here, it is one. With the R static, the result is better to see, okay? It compares for us already T1 to T2, T1 to T3, T1 to T4, T2 to T3, T2 to T4, and T3 to T4. And the P is here. It's easy for us to check. But for the base stat, okay, T1 to T2, 1. T1 to T3, 1. T1 to T4, 0.4, the same. Okay. T2 to T3, 1, same. T2 to T4, the same. And T3, 4, the same. All right. So whether they are written in the start base or the R statics or whatever other function in different library, okay, the principle is the same, and therefore the result also the same. It's just a matter of rounding. If you round, then it's a little bit different. A little bit different of the decimal number. Okay. All right. Any question regarding the Friedman? Any question? Any question? No? If no questions, I would like to have one of you to do the exercise, okay? And this time, okay, listen carefully. Decide, okay? Decide if you would like to have a 3 pair, okay? 3 independent groups or 4 independent groups is up to you, okay? So let's think just a few seconds and answer to me, any one of you, okay? All right, now, you want 3 dependents or 4 dependents as in what I'm doing? Just tell me first, 3 or 4 dependent? Anyone?
Maybe
Anyone? 3,
I will
okay.
be, sir. Yes.
All right, okay. 3 dependent groups, okay? 3 dependent groups. What quantitative variable you would like to do? Age or no, not age, okay? Score or like performance or whatever.
Let's try height, sir.
Height. So height, if you measure the same student, okay, maybe just different in time, okay? So the first year, and then you measure for the second year, the same student, the third year, okay, let's say height, okay? Height, okay, in centimeters, cm, okay? Okay, so this is the height and group here, let's say, university student, okay? Student, year 1 to year 3. We don't use year 4, okay? Now, for your practice, generate, okay, 25 students in year 1, a not normal distribution data, okay, one set, and you generate another one using different mean. You know what I mean? In my practice, I'm showing you, I generate just only one time, 100 sample, and then I divide. But here, you generate each time for each year. So first year, year 1, okay, you generate for 25 student or 30, let's say 30 student, okay? You say, okay, R, none, norm, okay? Then I say 30 student mean, okay? Let's say when they're in year 1, okay, let's say all male, no, not female, okay? 160 centimeters, okay, 1.6 on average, okay? And standard deviation equal. If you do not use the letter n mean, you can just use this, it's okay, okay? But just make sure it is in order. So standard deviation, 10 centimeters, okay? And Qness, like 8, and then GERD is 0. So this is a quantitative variables for year 1, height of year 1 student. And next year, you measure again, okay? All right. Okay. And then you need to put that here because we select only the data. Okay. Okay. Here. So I have here one student here, the first height here, but you can also round. Okay, make a round. I can round here. Easy. Okay, easy to just 1 or maybe 2. Okay. When you round it, short to decimal. Okay, here. Okay. Okay, so I made a sample for you already. So you need to generate year 2 and then year 3, and then you generate ID and also the nominal factors year 1, year 2, year 3. Okay, let's do it now. Take some time, and then after that you can share screen. Maybe take let's say 5 minutes. Okay, 5 minutes. Do it.
Sir, I have a question, sir.
Yes, please.
In the year 2 and 3, sir, should we use the same number of samples, like the n is 30?
Yeah, for the sample, because it is a dependent, we're using the Friedman, it must be dependent. So it must be same, 30, 30, 30. If you
Alright, sir.
want to have a significant difference, maybe you need to change the mean. So the first year, they're shorter. The second year, maybe they're higher. Or maybe the second year is not different, 165. And then for the year 3, you have 170, something like that, or 75, something like that. Okay?
All right, sir.
Yeah.
So should we also change the skew and curve, sir, as well as testing?
Yeah, it depends on you because it is not normally distributed data, so you can change.
All right,
Or
sir.
you can use the same, it's okay.
All right, thank you, sir.
Yeah. Anyone finish? Ryan, finish?
Not yet, sir. I don't even know if I'm doing the right thing, sir.
Okay. Maybe you can share and then we can go together.
All right, sir.
Okay,
That's
good.
fine.
Yeah.
Can you see my screen, sir?
Yes, yes.
Okay, so here is the Y1. I changed the number of the mean, sir, or the n, as well as
Okay.
the mean.
Mhm.
And
I
I just
think in terms of height, to be more logical, the first year maybe 150, and then second year 60, and third year 70. more logical.
all right, sir.
in terms
So
of-
that's
yeah.
60 and 7.
Good.
Maybe,
Right.
I'll rerun it, sir. Thank you.
Or maybe the third year 75 or 65, 165 or 75. Third year 3. The mean.
170.
Yeah, let's say 70. All right. So year measures, yes, okay. T1, T2, T3, E, okay.
Yes, sir.
ID, all right, good. And
So I'm here already, sir. I just copied this code from the above code, sir, and I'm trying to change it to this.
you need to combine the height of year 1, year 2, year 3 together. So on line 92, you put another one. You enter line 42. 92, yeah. So here you say height, yeah, height, and then equal C, concatenate year 1, comma, year 3, comma, year 3, C, comma, open bracket.
C?
Open bracket first.
Yes, sir.
No, round bracket, not square. Concatenate, yeah. Okay, so Y1, comma, Y2, comma, Y3. No need apostrophe because
sir.
they are number, yeah.
So Y1,
Yeah.
Y2,
Yeah,
Y3.
Okay, you can run, then you get the height data. Okay,
Yes, sir.
so 90. Okay, so year measures. So year here, maybe I think it's better to use Y instead of T. So Y1, Y2, Y3, big Y, big
Okay,
capital.
sir.
Okay. So each of the Y, so Y1 represent like the Y, small y here, so the number. And ID, okay, good. And then DF, maybe DF high, DFH, rather than DFCH because we have that already. Yeah,
Okay, sir,
just, yeah, okay,
DFH.
good. Yeah.
ID here, these two measures.
Mhm.
Yeah, it's right, sir, though.
Yeah, so year measures and then height.
Height, sir.
Yeah, no good.
And then let's run this one.
Okay. Maybe you just select first as data frame. So, okay, can you browse DFH? Okay, good. All right. And you can do the convert to numeric. So that is height, not the score. Mhm. And you also change the first DF. So DF as
H.
yeah, okay, good.
And the height, sir.
Yeah. Good.
Should I run this one, sir?
Sure.
All right.
Okay, and then that you need to change as well, the DF. Okay, and group. That is the
Year
years,
measure.
right? Yeah, measures. Okay, and
This
then
one's height.
grouped by, yeah, right, height. Then you can run.
And run, sir.
Yeah.
So
Okay,
So here's the p value.
they are normal. How can that be like that? So the first one,
The first one here we have the
So-
p value of 0.198, followed by 0.08 and 0.3, which
they're all
is
normal. Yeah.
yes, sir, normal, sir.
Can you just check the because it's R non-norm? You can say like Shapiro and then Y1. Can you check that? It should be not normal. Yeah. Okay. And Y1. Just okay, run.
Yes, it's normal, sir.
So 30 so 10 round. So here's the Shapiro's. So 30, it should be. So 10 standard deviation 10, and then 2. I do it here, it's not normal. I don't know why. So round air not norm, 30, 160, and then 10.
Yes, sir. I have also tried your codes earlier, sir, and it shows me different digits and data.
By the way, can you run the Y1, Y2 again?
This one, sir.
Yeah, right. Yeah, run it again.
Okay.
Y2.
Y2.
Yeah.
And Y3.
And can you run Shapiro just Y2?
0.09, sir.
Oh, still. Yeah, it's a high channel having normal distribution. Good. I think it's better to put a high standard deviation, maybe a 20 standard deviation.
20.
Yep.
This one, sir, no? This 10 is in 20.
Yeah.
Okay, sir.
Then you can run again.
Okay, sir.
Yeah, and you can just check the
And
yeah,
the Shabra again.
Yeah.
Sir, 0.12, sir.
and Y1 again. Check if any one of them.
Sir,
Okay,
0.00.
Yeah, so you can run 92 height. Okay, run height
Yes,
again,
sir.
height again. Yeah.
Okay.
All right. Okay, run all again. Okay. Okay.
Here, sir.
Okay, good. Yeah. So now it meets the condition of using the Friedman. Okay. Let's do
Yes, sir.
your Friedman.
Yes, sir. So when using Friedman, sir, it should be the p value. Not every p values should
Yeah,
be
yeah.
should be not
Right.
normal.
Just one is enough to use
Yes,
the
sir.
yeah.
Friedman.
Good.
So let's try the
Okay. Yeah.
the Friedman. Let me just copy this one, sir. Now.
Yeah. So R is somehow is easy like that. You can just copy, change the code, but make sure that you copy the correct one. Okay.
I don't know if this one is correct.
Maybe just one. Yeah, just
the
one.
top.
Okay. Yeah.
The test score should be high,
Yes. Height.
and time test it should be here measure
Yes. And ID.
and
The
ID.
same. Yeah.
Run.
Okay. And there is, of course,
The p value
because
is
because year 1 is just only 1.5 meters in mean. Okay, now you can say there is a significant difference in height of the student year 1, year 2, and year 3.
yes, sir.
And you can do a box plot to see.
Okay, so
Yeah.
that's size and box plot, sir.
Yeah, I can 100% believe that the year 3 have a higher height.
Tama ba yun?
Yeah, box plot.
It's a page. The score. Height.
Height. Yeah.
Yes, sir. And DF. Location. Dollar sign. Year measure.
Right.
Okay. Here, sir.
Okay, make it a bit.
Box plot.
Yeah. Okay, so yeah. Can you guess between the 3 pairs which one is significant? To me, year 1, year 3. I don't know.
Yes, sir. There's a significant difference between the year 1 and year 3.
It is a possibility of year 1 and year 2, but for me, it's just only year 1 and year 3. Year 1 and year 2, maybe 0.05 something or 0.06. Okay, let's see
Yes,
the pairwise. Okay, do the pairwise. I hope
Yes,
others
sir.
understand and follow us. Okay, it is a good practice.
Let's say that me
Yeah, just copy.
the
Using the R static is better to see. It's good to check the result.
This
Yeah.
The one with the home, sir, no?
Yeah.
All right. Let's just copy and paste it.
Yeah.
So this, okay, let's see this one first. So with the age,
from the beginning.
everyone's
Age,
score is
and
height.
then height, and then time is
That's the year
year
measure.
measure, and that's all.
Very, yeah, true, sir.
Mhm.
So let's run this one.
Yeah.
Okay, sir. So here's the,
Okay, yeah. Let what we think, right?
yes, sir.
Only
Year
year
one and
1 and
year
year
two
3.
is not significant. Year 1 and year 3 is significant.
All right.
And
So
year
when
2 and year
you-
3 not significant.
Yeah. And when you do your real exercise for your result in your research thesis or project, you need to be deep into this level, okay? So you said that the overall result among the 3 years, there is a significant difference. But what make it is different is between the year 1 and year 3, and the other years, they have no significance at all, okay? Until now, you understand why a post-hoc is crucial, right? If you do not do the post-hoc, we do not know which pair is different, okay? That's why we need to do a post-hoc. Among
Yes,
the
sir.
3 pairs, just only one pair, like in this case, has a significant difference, then it leads to the overall significant difference of the test, okay? So the overall significance of the test can be resulted from one pair significant difference, or 2 pairs, or all the 3 pairs. But at least one of them is significant difference that lead to the overall significance of the test.